Up to now, we have explored covalent and ionic bonds. These are bonds existing between atoms within a single molecule. We call them intramolecular bonds. They hold the molecule together and give it its special properties. However, what if we were to now take trillions upon trillions of these molecules and bring them close to one another? And trillions is quite a large understatement anyways. Just a single droplet of water contains 1.67 sextrillion molecules of water, just to emphasize the minuscule scale of atomics. But so what if we took a very large number of molecules and brought them together? From our knowledge, we know that these molecules will stick with one another and form a piece of matter. If we were to bring a bunch of water molecules together, we would form a body of water. If we were to bring a bunch of salt molecules together, we would form a salt crystal. Bringing a bunch of silicon dioxide molecules would form a block of quartz. But how come these molecules are deciding to stick with one another? To explain this, we introduce the idea of intermolecular forces. The bonds we discussed earlier, covalent, ionic, those are all intramolecular forces, bonds existing within a single molecule. Intermolecular forces differ greatly, as they are forces of attraction between molecules. And so make sure that we're paying attention to the difference between intra and inter. Intra is going to be within a molecule, inter is going to be between molecules. Just like we have multiple types of intramolecular forces, we also have many intermolecular forces, and they all differ in strength. Let's go over the 5 main ones, ranking them from weakest to strongest. Starting off, we have London dispersion forces, or LDFs for short. I'm not going to do a deep dive into quantum physics in this video, but I do want to explain some interesting characteristics about the atom so that you can truly understand and appreciate London dispersion forces. When drawing our Bohr model of the atom, the one that I've pictured here below, with rings denoting energy levels, you need to realize that it's pretty wrong and doesn't align with our actual understanding of the atom. You see, electrons do not have defined energy levels. Instead, they are constantly jumping between sublevels, and this forms what we call an electron cloud. As you can see by this image, we have our red nucleus surrounded by our electron cloud. The reason you need to know this is the following. Our electrons in the electron cloud are not always distributed equally like they are in this photo. If we were to draw a general shape around our electron cloud in this photo, it'd be a pretty nice circle. However, sometimes there may be more electrons here, and other times there may be more electrons here. This is all due to the random nature of the movement of our electrons. But so let's say that there were more electrons in here at a single moment and less here. This would change the shape of our cloud, as there would be more density in one region. This means that we have brief moments in time when our atom is more electronegative on one side than it is on the other, which creates partial positive and partial negative charges within our atom. This is known as a temporary dipole, and it is how London dispersion forces arise amongst molecules. Take note that the definition of a dipole in chemistry is when a concentration of positive electric charge is separated from a concentration of negative charge. So now to truly picture how a London dispersion force forms, imagine we have one atom here and another atom here. As you can see, the electron clouds of both of these atoms is going through instantaneous moments where they are unequal. What's going to happen is that the left atom's more positive region is going to attract to the right atom's more negative region, and so these molecules will attract to one another. This is a London dispersion force happening. This is our actual attraction between our molecules. The unbalanced electron clouds of molecules will attract one another, thus forming brief moments of intermolecular attraction. And that right there is the definition that you really need to keep in mind when it comes to London dispersion forces. You need to realize that because our electron clouds are not always completely evenly distributed, there's going to be brief moments of polarity, and when this happens amongst many molecules, they will attract to one another's brief moments of polarity. London dispersion forces are important as they are the only form of attraction between nonpolar molecules. It's also important to note that as the size of our molecule grows, so does the strength of our London dispersion forces. This is because larger molecules will have larger electron clouds, and thus stronger moments of polarity. Dipole-dipole interactions are the next step up, and they arise amongst molecules containing permanent dipoles, which, just to remember, dipoles are the separation of our positive and negative charges in a molecule. Because dipole-dipole interactions happen amongst molecules containing permanent dipoles, these are going to be molecules that are polar. For instance, carbon monoxide. Because oxygen is more electronegative than carbon, in the electron cloud, it will attract far greater electrons than carbon will. And so oxygen will have a partial negative charge, and carbon will have a partial positive charge, showing polarity in the molecule. If we then have multiple of these molecules present with one another, attractions between their dipoles will occur, thus forming dipole-to-dipole interactions. Dipole-dipole interactions are stronger than London dispersion forces because the permanent dipoles are more polar in charge than the temporary dipoles found in LDFs. And just to simplify that, they're stronger than London dispersion forces because the polar bonds they contain are going to result in more polar electron clouds than just temporary dipoles, which are what London dispersion forces contain. There is also a sort of mix between London dispersion forces and dipole-dipole interactions that exist, and we call these dipole-induced dipole interactions. You're not expected to know these on the AP exam, but just so that you aren't completely ignorant of their existence, these are intermolecular forces which exist between a polar molecule and a nonpolar molecule. Nonpolar molecules, such as fluorine gas, which I've drawn here on the right, of course, normally have beautiful electron clouds like this one. But just like we see in London dispersion forces, these electron clouds can have moments of polarity where we get varying charges. When this happens with a polar molecule in the vicinity, they will attract one another, and we will get a dipole-induced dipole intermolecular force of attraction. Our next intermolecular force of attraction are hydrogen bonds. I have a full video over this on my channel already, and so I recommend you check that out for more information. The key takeaway for hydrogen bonds is 1. They are not bonds, they are intermolecular forces. And number 2, they only exist when a hydrogen, which is bonded to either a nitrogen, oxygen, or fluorine, forms a temporary attraction with either another nitrogen, oxygen, or fluorine. This solid line here denotes the hydrogen bonded to an oxygen, and this dashed line denotes the hydrogen bond to the fluorine. Additionally, you should know that hydrogen bonds are much stronger than dipole-dipole interactions because the very negative either oxygen, nitrogen, or fluorine atom, when compared to hydrogen, results in a very large difference in electronegativity, resulting in a very polarized electron cloud. The last intermolecular force we will talk about are ion-to-dipole interactions. These occur when an ion interacts with a polar molecule, such as when we dissolve a salt in water. Ion-dipole interactions are actually the reason that salts are soluble. They are the strongest of all our interactions because ions already contain very polar charges, and so do polar molecules. So if we pit those against one another, we get a very strong force of attraction, strong enough to rip a salt in its solid form into its separate ions within a solution, thus effectively dissolving it. Just to show you how an ion-dipole interaction might work, imagine that we have our NaCl molecule. Sodium is our cation, and chlorine is our anion. If we then surround this by water molecules, the water will be attracted to the charges of our sodium chloride. Remember that our oxygen has a partial negative charge, and so it will attract to our positive sodium cation. Hydrogen has a partial positive charge, and so it will be attracted to our negative chlorine anion. The forces of attraction of these water molecules will be strong enough to cleave our bond between sodium and chlorine, thus ripping the ionic solid into its separate ions. This is what's actually happening when we are dissolving a salt in water. I know that those 5 intermolecular forces were a ton of information to take in at once, so let me again write these down in order from weakest to strongest. So just to repeat, London dispersion forces are our weakest, followed by dipole-induced dipole, dipole-dipole, hydrogen bonds, and then ending with ion-dipole interactions being our strongest. Another thing we can do is to group London dispersion forces, dipole-induced dipoles, and dipole-dipoles into a common group, which we call van der Waals forces. I just want you to be aware of this distinction in case it arises on an assignment. For the next part of this video, let's understand the significance of these intermolecular forces, specifically the importance of their differing strengths. As the strength of the intermolecular forces in our substance increases, so does our boiling point, melting point, viscosity, and the surface tension of our substance. Pretty much what we're saying here is that as the forces of attraction between molecules are getting stronger, the physical properties of that substance is also changing. That's something I think is really cool to realize. It's important that you realize that this is the case, this is all happening, because higher intermolecular forces will require more energy to overcome. It takes a lot more energy to break a hydrogen bond than it takes to break a London dispersion force. Vapor pressure is the pressure exerted by a substance's vapor when it is at equilibrium at a given temperature. This equilibrium occurs when our rate of evaporation is equal to our rate of condensation. Volatility is the tendency of a molecule to evaporate or form a gas. As we lower the strengths of our intermolecular forces, both of these values will increase, as it's going to take less energy to break the forces holding our molecules together. So substances containing London dispersion forces will form gases easier, and at equilibrium, a higher amount of the substance will have evaporated. This is why gasoline easily evaporates indoors. It's a nonpolar molecule, and so we know it only contains London dispersion forces holding its molecules together, which is a very weak intermolecular force. It's the weakest out of all of them. We would say that it has a high vapor pressure and high volatility, so a lot of it is going to evaporate. The very last thing you need to understand in this video is what happens when we break intermolecular forces. Imagine again we have carbon and oxygen connected by a single bond. If we were to break this bond, we would be creating two new molecules, carbon and oxygen. And so we would say that a chemical change has taken place. However, the breaking of intermolecular forces is not a chemical change whatsoever, because intermolecular forces are not permanent. Write that down, underline it, start, highlight it. You need to know that intermolecular forces are not permanent whatsoever. They are forming and breaking by themselves constantly and at an incredible rate. In fact, the average London dispersion force lasts for just 10 raised to the negative 15th seconds. That's this many seconds. When we break or form enough intermolecular forces, we say that a phase change or a physical change has taken place. I'm hoping that some of you just let out some oohs and ahs. Intermolecular forces explain the physical states that matter falls into. And with that said, that's absolutely everything that you need to know about intermolecular forces for your chemistry class. I hope that this video was informative and not too confusing or long. If there were any parts you didn't understand, I recommend rewatching those portions of the video. If you're still not getting it, take a break and come back after. Thank you so much for watching.